is just a generic graph. I'm not going to give us the equation of the graph. I am just going to call that f of x. So we've been talking about so far, we've been given numbers and we've been asked to estimate that area under f of x. So we're breaking it up into a bunch of rectangles and adding up the areas of those rectangles. And we've been doing that, and that's a Riemann sum. When we're breaking that up into rectangles, adding up the rectangles. And I just want to pause for a second to talk a little bit about notation. So if I put a generic rectangle in here, and I almost drew a left-hand endpoint, I'm going to go ahead and draw a right-hand endpoint, because for those of you that were in Chidori's lecture yesterday, I was very relieved to hear that he said, you can use right-hand endpoints whenever you're asked to do the limit definition for the integral. The right-hand endpoints usually work out a little more nicely. So I'm just going to call this my ith area, right? So if we're thinking about, I've got this chopped up into a bunch of little rectangles, but I'm going to take generically that ith one. And the way that we've been looking at this in terms of notation is to say for that generic ith rectangle, we're going to find that area of the rectangle by looking at a height times a base. And I like to use base and height because length and width for a rectangle, some people see this side as the width and some people see this side as the length. But using height and base, usually that's pretty clear. So we've got formulas, and we talked about where those formulas come from last time. But the base of my rectangle is going to be that little bit of delta x. And that delta x is going to come from looking at the entire width of my interval. So here that would be b minus a divided by n, because we're talking about n rectangles. So again, I'm just kind of reviewing the notation stuff here. So we've got n rectangles. So that base for each rectangle, or that delta x, is going to be minus a over n. Now to get the height of that rectangle, we need to know what's sort of the generic x value that we're sitting at. We talked through this a little bit last time, but for my ith rectangle, if we look at the right-hand endpoint, then at that right-hand endpoint, that x value that our book sometimes denotes as x star, or they give it an x with a subscript of I. But that x value comes from, I'm starting at A, and by the time I get to the right-hand side of my ith rectangle, I have moved over I copies of that delta x width, or I delta x. So in terms of my height, that's coming from plugging in this, the a plus I delta x, into the function. Now, if I wanted to find the true, actual, correct area, not just an approximation, and I want each of those little bits of error to go away, then what we do is we take this Riemann sum and we take the limit as n approaches infinity, meaning we're going to shove an infinite number of rectangles in there. And when we do that, the width of each rectangle will shrink down to 0. So there are two ways that we write that in our 17B textbook. It's usually just written as the limit as n approaches infinity. If you've had calculus before in a previous life, or if you have a different calculus textbook other than the one we're using, sometimes this gets written as the width of the partition goes to 0. And if you have friends who are taking the 21 series for calculus, this is how we write it in the 21 series. But I'm going to stick with what I think is friendlier notation of that limit approaching infinity. Okay. Now we're going to switch gears, and pretty much for the rest of the quarter, we're going to get rid of this clunky notation And we are going to switch over to using what we call integral notation when we're talking about definite integrals. So I'm going to take this same picture and draw in my generic rectangle. But this time, I'm going to think about this as, well, if I want to find the area of that rectangle, I still need a height times a base. But notation-wise, what we're going to do here is I'm going to say, well, I know that that n is approaching infinity, or that that width of the partition is going to 0. Well, if this shrinks down to 0, we're going to use the same notation we did in 17a. When we were first talking limit definition of the derivative, we had a delta x. And when we took that delta x and we shrunk that down to 0, when we took the limit as delta x approaches 0, we called it dx. And that's the notation that we use with derivatives. And that's the notation we're going to use here. So the width of my rectangle, we know it's going to 0, so we're going to call it a dx. Well, how would I find the height of that rectangle? Well, this height for any given x value is just that f of x. So when I go to write in our prettier notation, the height of that rectangle is f of x. And my base of the rectangle is a little bit of dx. We're going to add those up calculus style. And an addition problem is also called a sum. And sum starts with s. The other thing that we have to do that here is taken into account by the width of the partition and then taking n partitions to get what our bounds are. Here, we need a way to incorporate those bounds as well. So notation-wise, we say that we're going from A to B. So I would read this as the definite integral of f of x from A to B. So this notation here says we have a function, and the function we're working with is x squared plus 1. So if I wanted to draw a picture, I absolutely can. I highly recommend drawing at least fake pictures. So x squared plus 1, I know that's a parabola. It's shifted up 1 and it's concave up. It doesn't have to be perfect, just something to kind of wrap your head around what's going on. And this notation says my rectangles are going to go from 1 to 5. So I'll draw in x equals 1 and draw in x equals 5. Right now, I'm asking for an estimate. So that estimate means that we're going to be using a Riemann sum. We're going to be talking about rectangles. Here I've got 4 rectangles. So if I break up the interval from 1 to 5 into 4 pieces, those are going to have x values of 2, 3, and 4 in the middle. So the 1, 2, 3, 4, and 5. So those are my 4 intervals to form my rectangles. And then here, we've been told to use midpoints. This could be replaced with left hand, or this could be replaced with right hand, or this could be replaced with upper or lower. But right now we've been told midpoints. And that just tells us where to find the y values to form the heights of our rectangles. So I'm going to look in each of these intervals. I'm going to get rid of my x equals because it's a little bit messy down there. And I'm going to look at the midpoint for each of those. So the midpoint of 1 and 2 would be 1.5. So when I find the area of my first rectangle, I'm going to use 1.5 as the value that I plug in to get the height. So that first rectangle would look like 1.5 squared plus 1. That's my height of the rectangle. And then the base of my rectangle, I didn't actually do yet, but to get that delta x, remember I'm doing b minus a over n. So I'd have 5 minus 1 over 4, or my delta x is 1. Here's my base and my height. Because the base is the same for all of the rectangles, I'll go ahead and keep it factored out. So this is the height for my first rectangle. The height for my second rectangle, again, I need the midpoint or the x value that's in between 2 and 3. So 2.5. I can do math today. So I would have, oh, already got some parentheses there. So I'd have 2.5 squared plus 1. The next one, I'd be at 3.5 for that midpoint squared. Having trouble with parentheses this morning. And then for the last one, I'd be at 4.5. We'll just give myself extra parentheses because I wrote some extra parentheses there. If we wanted to use left-hand endpoints, then the numbers that we would be plugging in for x would be the 1, 2, 3, and 4. And if I wanted right-hand endpoints, then the numbers I would be plugging in for x are 2, 3, 4, and 5. One of the things to note is that if I'm using 4 rectangles, then I'm only ever using 4 of the x values. So even though, like if we were doing left-hand endpoints, if we draw it out, we might have the, we might draw it with the 1, 2, 3, 4, and 5. That's like 5 x values. But those 5 x values don't really give us 5 we'd get a 5th rectangle if we used 5 of those. So there's a question in the chat about why did we take, oh, the 1, got it. Okay, so this is my delta x. And for all of my rectangles, to get the area, I need the height times the base. But since the base of all of the rectangles is 1, I just factored it out. You could also write it each time. You could write it as 1 times the 1.5 squared plus 1, and then 1 times 2.5 squared plus 1, right? And keep going. It's just a choice. So if we traded out the word midpoint for, I'm going to abbreviate left hand. So if I were to use left hand endpoints, then again, my delta x, my width for each rectangle is still a 1. But now to get my heights, I'd start on the left hand side and use, I'm going to be lazy here, f of 1, and then f of 2, f of 3, f of 4. If I were doing right hand endpoints, again, I'd have a 1 for my base of each rectangle, and then my height, if I were doing right hand endpoints, I always think about it as starting on the right hand side, and I know that I need to use 4 values for x because I'm doing 4 rectangles. So if I started on the right hand side, I'd use 5, 4, 3, and 2. So I'd have f of 2 plus f of 3 plus f of 4 plus f of 5. So the difference here, if I need to actually evaluate that integral, we have 3 options, right? And Chad already talked about those 3 options. Sometimes we've got geometry formulas that we can use. In this case, there actually is a geometry formula for the area under a parabola, but I don't think it's one that most of us learn. So there's the geometry piece of it. There's something that's going to involve antiderivatives, but we'll get there in section 5.3. At this point, our only option, if we're going to evaluate this, is to write the Riemann sum and to let the number of rectangles go to infinity. So let's practice that. And we're not going to finish it all the way out, but we can set it up and practice with the notation. So I know that notation wise, this is going to be the same as taking the limit as n approaches infinity. We're going to go from I equals 1 to n, and the pieces that we need to put in here, I'm just going to abbreviate as f of x sub I times delta x. And then we're going to replace the x sub I, and we're going to replace the delta x with what they are in this particular problem. So for my delta x, I'm going to find that by doing 5 minus 1 divided by my number of rectangles. But if we're evaluating this, we're going to let the number of rectangles be equal to n. Then we're going to take the limit as n approaches infinity. So right now, my number of rectangles is n. So I'll swap out that delta x for 4 over n. Still going I equals 1 to n. Now my function, I can get the function ready to go because I know it's x squared plus 1. I might need a little bit more space here. So I'm going to need my x squared plus 1. And my delta x was 4 over n. So this is like my height. And that's my base. But to get what I would plug in here for that x sub I, that's where we're going to need that formula. And again, we talked about where that formula comes from last time, but we build off of, to get my generic rectangle here, on the right-hand endpoint, I start at my lower bound. So I start at 1. And by the time I'm on my ith rectangle, we've moved over I times our delta x. So I'd come in here and plug in 1 plus I times 4 over n. And I've got a ton of parentheses in there. We probably don't need all of them. But this is how I would represent this true accurate integral. The value for the area under the curve is equal to this. I'm going to point out something that was said in lecture on Monday. We don't have to actually work out the summation for this. Read this as the definite integral of natural log of x plus 1 from 0 to e. And if I wanted to write this as the limit of a Riemann sum, then this is equal to, I'll get my limit going here, the limit as n approaches infinity of the sum from I equals 1 to n. Wish I had like a stamp to put that part on there because that piece never changes. Now, the two pieces that I have to actually fill in, I know that I need to find f of x I, and I need to find my delta x. So these are the two pieces that we have to find for the given problem. So my delta x, I'm going to get by doing e minus 0 divided by n, or e over n. And then I'm going to get my x sub I by taking my starting point of 0 and adding to that I times delta x, or e over n. So the question in the chat is essentially like, what would we call this? So absolutely. The question might say that we're going to express the definite integral as the limit of a Riemann sum, or just write the definite integral as the limit of a Riemann sum. So here's my x sub I, and I'm going to simplify that around, and I'm going to say that's ei over n, and plug it in here. So I'd have the limit as n approaches infinity, my sum from I equals 1 to n. This is my x value that I'm plugging into the function. So I'd have natural log of ei over n. Oops, I almost lost my plus 1. Plus 1, and then times my delta x of e over n. So if we're going to express this as an integral, and we think about that integration notation that we have, I've got my summation thing. We're going to have to figure out what was the a and the b. And then we're going to have to figure out what's the function. And dx we get for free. We know it, so it always has to be there. That's my delta x. That's my width. So we look at the example that was given, this thing floating out here, well, that kind of has to be my delta x. So that, if we're working this backwards, just told me that the total width of my interval has to be 1, right? So the difference between a and b has to be 1. I now know that b minus a is equal to 1. Now I'm going to look at this. When I look at that, the function that I see that's kind of jumping out to me is 1 over 1 plus x squared. That's the function that I see when I look at that. Well, if that's 1 over 1 plus x squared, and I know that my b minus a has to be equal to 1, if I look at this part in here that's being squared, there isn't like a number plus I times delta x, right? There isn't kind of a number in there. If you had to put a number in there, it's a 0. It's an invisible 0. So that's telling me that my a was equal to 0. And if b minus a is equal to 1, then my upper bound must be a 1. This one's actually really interesting, but I'm going to start by looking for that delta x piece. So that's the 3 over n. That's my delta x. And since that has to be b minus a over n, that's telling me that b minus a is equal to 3. Or whatever else is going on, this difference between the a and b has to be equal to 3. Now the next part comes down to, what do we think the function is? So I'm going to give everybody a second. Looking at this, that's some kind of function. But if you had to write it as f of x equals, what do you think the function is? Go ahead and type it in the chat. And exactly what I was hoping would happen happened. Sweet. Okay, so people put in a bunch of different answers, but really there are kind of 2 answers that are showing up for people, and that's what I was hoping. Some of you looked at this and saw that as f of x is equal to the square root of 2 minus x. But others looked at that and saw this as f of x is equal to the square root of x. And you're both right. Okay, I think this one is probably the more natural looking one that we might see in there. But I was trying to decide which one to start with. I'm going to start with this one. So if you look at this and see the function as the square root of 2 minus x, then I know that our rule for what that x sub I should look like is a plus I times delta x. Well, we've already figured out that our delta x was 3 over n. So I'd have I times 3 over n, and then plus something. Well, if I think the function is 2 minus x, then 3i over n is the x. And if 3i over n is the x, then that means a had to be 0. Which means that if we express this as an integral, my a is 0. The width of that entire interval has to be 3. So this would be 0 to 3 of the square root of 2 minus x dx. And that is perfect and correct. And I realized as I was working through this problem that this was a terrible example and I shouldn't have put a minus sign in there. So I'm going to skip this part. Though I do appreciate that people saw that it would work as just the square root of x. I'm just going to leave it at that. Here's my function, 0 to 3. I hope that helped in terms of where the 0 came from, but I still see more questions about the 0. So clearly it didn't. Let me try again. If I have to work one of these backwards, then my first step is to figure out what was my delta x, and my second step is to figure out what the function is. Once I know the delta x and the function, then that's going to determine what this formula has to look like. So once I decide that the function is 2 minus x, then looking at what we have in our summation notation, 3i over n, that has to be equal to my x sub I. So I can't have another, there isn't another number here. So the invisible number there is going to have to be a 0. I don't know if that's helping. We can do another example. So 3i over n is my xi. 3 over n is my delta x. But because this is like the x from my function, there isn't an extra like plus something. So we're sort of stuck with that. Okay, let's move on. Let's do some signed area. But don't take notes on this for a second. Just watch. Because I continue to get questions about this square root of x thing. I'm changing the problem. Do not take notes. I'm going to go through and everywhere that there's a minus sign, turn it into a plus for a second. Okay, I meant to have that look like a plus. So if that were a plus, then the other option that we could have done here for a function, so this is for our f of x being equal to the square root of 2 plus x. But if I saw this as my function being the square root of x, then my x sub I, which would look like a plus I delta x, if I look at what I had was 2 plus 3i over n. So this time, because my function was just the square root of x, it means we would take everything under the square root and call that x. Well, once we do that, that determines that my a is equal to 2. So if I wrote it this way, then my integral would go from 2 to 5 of the square root of x dx. I had y equals square root of 2 plus x. And, oh, I need an equal sign. Awesome. And y equals just the square root of x. And someone showed me this trick the other day, and I'm going to try to make it work. So on the first one, we want only the part from 0 to 3. And here, we wanted only the part from 2 to 5. So hopefully you can see this okay, but they're the same thing, we're just shifted over. So if I think about, let me grab a color here. So if I think about the area from 0 to 3 underneath this guy, we get exactly the same shape as if we were doing the area from 2 to 5 under this one. So even though the definite integrals look pretty different, those definite integrals are just a representation of that area under the curve, and the areas for both of those are identical. This, yes, we could write out a Riemann sum for it, but that's not what we're going to do. We're going to evaluate as signed areas. What that means is I'm going to look at this definite integral, and I'm going to start by graphing my function. So here the function is the absolute value of x minus 2. And definitely, if you're doing your homework, grab Desmos, grab a graphing calculator, do what you need to do to get these graphed. You're not going to be asked to do anything too crazy. I'm going to go with an absolute value graph isn't too crazy. This has a vertex at 2 and kind of looks like a big V. This, notation-wise, says that I'm looking for the area from over here at -1 to over here at 4. So evaluating this is equivalent to finding the area of these two pieces. Since both of those pieces are triangles, we've got a convenient formula in terms of finding that area. So for this piece over here, I know I need 1/2 the base times the height. Well, the base here is 3. And the height of that triangle I get by plugging -1 into the function. So -1 minus 2 puts me at -3. The absolute value bars give me a 3. Over here, I have another triangle, so I'll have 1/2. This time my base is 2. And my height I'm going to get by plugging in 4. So when I plug 4 into the function, 4 minus 2 is 2. Absolute value doesn't do anything. And the answer to this is, what's that? 9/2 plus 2. 9/2 plus 2. And I'll leave it alone.